In the previous video, we introduced the determinant of a 2 by 2 matrix and saw that it has a geometric interpretation, namely when a matrix transforms the unit square, the determinant tells us how the area changes. So for example, if the determinant of that matrix was 6, then every region would have its area multiplied by 6 once it's transformed by that matrix. Similarly, if the determinant is 1/2, then the areas are cut in half. All of the examples we saw in that video had matrices with positive determinants. So what we want to do now is, first of all, explore what happens, what it means if the determinant of a matrix is negative. And for that, we need to define this concept of the orientation of vectors in R2. So if we've got an ordered pair of vectors v1, v2 in R2, then we say that that pair is positively oriented if the angle measured counterclockwise from v1 to v2 is less than 180 degrees, and that the pair is negatively oriented if this angle is greater than 180 degrees. So you can see the first example on the left here, those vectors are positively oriented. When we go from v1 to v2 in the counterclockwise direction, the angle is less than 180. And in that second example here, we've got a negative. Those are negatively oriented. As we go from v1 to v2 in the counterclockwise direction, that angle is going to be greater than 180 degrees. Our unit square, we think of sort of, E1 as one of the sides being the vector 1, 0, and E2 being the vector 0, 1. So if we, sort of draw those out, we have E1, E2. And so those are going to be positively oriented, right? So the angle, as we go from E1 to E2, that angle is less than 180 degrees. If A transforms the unit square and transforms those vectors so that they end up being, after they're transformed, negatively oriented, then the determinant we would say is negative. So, the determinant still tells us something about, sort of how much the area gets scaled, but it also sort of tells us if the matrix transformation has some sort of like a flipping effect. And we'll see some examples in a minute. So just to sort of reiterate here, if we have a 2 by 2 matrix A whose columns are v1 and v2, then if the pair of vectors is positively oriented, the determinant of A is the area of the parallelogram formed by v1 and v2. And if the pair is negatively oriented, then the determinant is equal to the negative area of the parallelogram. So let's say A is the matrix 2, 1, 2, negative 1. So if we think of this as a matrix transformation, the first column tells us that E1 gets sent to the vector 2, 2. So 2, 2, right? So this is going to be the transformed version of E1, and then E2 gets sent to 1, negative 1. So you could see that the orientation got flipped, right? So this is, A1, and this is A, E2. And so now as we go from the transformed version of E1 to the transformed version of E2, that angle in the counterclockwise direction is greater than 180 degrees. So we get a negative orientation for those. If we were to think about the area of this particular, this transformation of the unit square, we could go ahead and compute it. It ends up to be sort of a rotated version of a rectangle where we've got, this side down here. A couple ways we could do this, but this side down here would have length √2 by the Pythagorean theorem. And then this side up here, I guess, would be square root of 8. And so the area of this is just going to be 4 √2 times √8, which is √16 which is 4. If we go ahead and compute the determinant of this matrix A, we get -2, or maybe I'll show the whole formula again just to remind you. So it's going to be AD minus BC, right? So 2 times -1 minus 1 times 2. So that's -2 minus 2. So it's -4. So we see that we get a negative value, and that is because E1 and E2 again ended up being after they got transformed negatively oriented. But we see that the absolute value of that determinant is going to still be +4. So if we take the absolute value of the determinant, whether it's positive or negative, it still tells us kind of that scaling factor. Let's look at another, just quick example here, a simple example where we are just vertically scaling things by 2. So our unit square ends up to be this rectangle here. The area of this can quickly compute and determine is just 1 times 2, so 2. And of course, the determinant of this matrix B is just equal to 2, 2 times 1 minus 0. But what we really want to look at is actually the transformation A times B. And so, if B vertically scales by 2, and A kind of does a whole bunch of things, right? There's some scaling, there's some rotating, there's this flipping action. So when we do A times B, first we're going to apply B, and so that's going to scale things up by 2 in the vertical direction, and then we're going to apply A, which is a scaling of everything by 4, and again, this rotation and this flipping. But what we want to kind of look at here is, so this is this image here is what happens to the unit square after first applying B, then applying A. And if we compute the area of this, right? So let's see. So the area of this, it would be, I guess, √8 and √8 are the two sides. This is a square. And so the area of this is just equal to 8. Notice that the area of this transformed unit square under A was 4. We scaled the area by 4. Under B, we scaled it by 2. So if we're looking at AB, we would sort of think about, okay, first we're scaling by 2, and then we're scaling by 4. So overall, we're scaling by 2 times 4, which is 8. And we can see that that's what happens here. The determinant of this AB matrix, we could compute. It would end up to just be, negative, so let's do this, 2 times -2 minus 2 times 2. So we get -4 minus 4, and we get -8. This happens again because A does that sort of flipping action. So we get a negative value, but you can see that it ends up to just be the determinant of, so I'll write the whole thing, the determinant of AB is just the determinant of A times the determinant of B, right? The determinant of A was -4, the determinant of B was 2. So we end up getting -8. And that's not a coincidence. That's going to be actually a general property of determinants. And hopefully here you can start to see why that happens when we're thinking geometrically and understanding this concept that the determinant somehow is scaling regions in R2, then when we're multiplying two matrices together, their matrix transformations, the determinant is ultimately going to say, okay, first we're going to scale by this amount, then this amount. And so if we do both transformations in a row, we're just going to scale in total by their product. And so that's reiterated here. Don't have to go through this again, but just so you can see, the determinant of AB, again, is the determinant of A times the determinant of B. For this example, it is true in general. In fact, we could show it, we've seen it geometrically, we could show it algebraically here just to really convince you that it's true in general, at least for 2x2 matrices, and then we'll talk more about larger matrices later on. But if we want to go through this, first we'll need to, sort of algebraically compute A times B. And some of this gets a little bit messy, which is why we don't just jump right into, showing this messiness always. Motivating it with the geometry is nice, but sometimes kind of going through the algebra is nice as well. So A times B, it's going to be A11 B11 plus A11 B21, and then A11 B12 plus A12 B22, and then A21 B11 plus A21, A22, A22 B21. Let's try not to go too quickly here. And then the last component of the product should be A21 B12 plus A22 B22. Okay. And so the determinant of AB is going to be AD minus BC, or whatever, the multiplying the components in the correct way to get the determinant. So A11 B11 plus A11 B21 times A21 B12 plus A22 B22 minus A11 B12 plus A12 B22 times A21 B11 plus A22 B21. So that's the determinant of AB. If we do the determinant of A times the determinant of B, we'd get A11 A22 minus A12 B A21, and then times B11 B22 minus B12 B21. So, algebraically, we'd want to see that these two things are equal, and they would be. I'm not going to go through all of the work, but because it would again just get even messier. But we'd want to essentially distribute enough to get these two formulas to look the same. And again, I'll sort of leave that as an exercise for those that are really into doing a lot of this messy algebra. But for our sake, I think seeing that we can do the algebra if we really wanted to, but kind of understanding the geometry is a bit more important for us. But I'll get you to this point, and then you can do all of the additional distributing and expanding and sort of making sure that these two things are indeed equal. Thinking about determinants in higher dimensions. So later in the section and in other videos, we're going to learn an algebraic technique for computing determinants. So far, we've mostly focused on the geometry, and we have our formula for 2x2 matrices, but we're going to look at higher matrices. But in the meantime, we simply note that determinants can be defined for n by n matrices by measuring volume. So for a 3x3 matrix, the columns determine a three-dimensional parallelepiped, it's called. So sort of the three-dimensional version of a parallelogram. And the determinant of a 3x3 matrix is related to the signed volume of the parallelepiped formed by its columns. So the image here shows you the parallelepiped for vectors, with three sides, basically v1, v2, and v3. So the volume of that parallelepiped would be what would equal the determinant of the matrix whose columns are v1, v2, and v3. And so, the formula for the determinant of a 3x3 matrix is a bit messy, but we do want to kind of just keep in mind that this is what's going on in the background. And some of the messiness just comes in because when we're doing formulas for volumes of these types of objects, and we have specific components, the actual nitty gritty of the algebra and the math can just ultimately get kind of messy. But keeping in mind this idea will help us when we're actually trying to apply the determinant in various settings. And just to reiterate, so for a 2x2 matrix, the determinant measures area scaling. For a 3x3 matrix, the determinant measures volume scaling. The same idea does extend to higher dimensions, although, thinking about 4 or 5 or 6 dimensional objects is the topic of other YouTube videos for sure, something that is certainly interesting to consider, but definitely challenging for us humans that, live on a planet in 3 spatial dimensions, and sort of, 2 or 3 dimensions are a bit easier for us to comprehend. But if you allow yourself to consider 4 or 5, however many dimensional objects, then the extension of this determinant idea, being the scaling of a 4 or 5 or 6 dimensional volume, is something that you can definitely do. Okay, and we want to end on this proposition 348, which just lists a few properties of determinants. The book does go into a little bit more in terms of kind of motivating some of these, but we'll leave those for other videos or for you to see in the book. But in general, we've got a few properties to list here. So the determinant satisfies the following properties. First of all, the determinant of a triangular matrix equals the product of its diagonal entries. This is a really important property that will help us when it comes to actually doing some computations of the determinant and understanding some applications and other properties. If P is obtained by interchanging 2 rows of the identity matrix, then the determinant of P equals -1. And so, the idea there is that if you interchange 2 rows, thinking geometrically at least, if you just go with the 2 by 2 case to kind of motivate this. So if we interchange our 2 rows of the identity matrix for a 2 by 2, our identity matrix for a 2 by 2, just to remind you, is this. If we interchange the 2 rows, we'd end up with this matrix. That transformation essentially would just be flip-flopping the x and the y, and so we would be reorienting things. So the orientation would change. We would end up getting a negative value. The same kind of idea extends to higher dimensions, 3 by 3, 4 by 4, so on and so forth. And then the last one here, that in general, the determinant of AB is the determinant of A times the determinant of B. We'll see that this again, is going to be a really important property for us. And, hopefully looking at the geometry and thinking about that scaling idea helps you understand why this is true and has to be the case. So we'll keep working with determinants, looking at how to actually compute them, but hopefully we have successfully motivated some of those concepts in these videos.